Welcome to Lesson 9C, Particle Concentrations, Part 1. We're going to introduce a few more definitions and terminology related to particles, and then we'll discuss some concentrations, mass concentration and number concentration, and a couple different kinds of average diameters. The first additional definition is aerosol, and aerosol is a suspension of particles in air. And I want you to remember that particle can be either a solid or a liquid. You can have liquid droplets, and people in the air pollution business still call those particles. Then a hydrosol is a suspension of particles in water, and that's also called sediment. We will use aerosols. Obviously, this course is air pollution, so we're going to use aerosols, not hydrosols. But all the equations and the definitions for aerosols will apply also to hydrosols. So if you do any civil engineering applications with sediment, all the equations that we derive here will still hold. For gases, all the particles of species J, the particles here are molecules, are the same size. But an aerosol can have particles with a range of sizes or diameters. So there's two other definitions, monodisperse and polydisperse. Monodisperse aerosol means that all the particles are the same diameter. And this does not really occur in nature. Polydisperse aerosols mean that the particles are not all the same diameter, but there's usually some range of diameter. And that's what we typically find in nature. And when you have a polydisperse aerosol, you have to define some statistics that relate to the distribution of the particle sizes. And we'll also do that in terms of sizes or masses. So we'll typically have polydisperse aerosols in our examples, but we're going to use monodisperse to derive some equations to make it simpler. So next I want to talk about types of concentrations of particles. First of all, recall that for gases we use mole fraction or mass concentration or molar concentration. And I list the units for each of those. Mole fraction is ppm, and then mass concentration is milligram per meter cubed or microgram per meter cubed. Molar concentration is in mole per meter cubed, kilomole per meter cubed. Now, of these, if we're talking about particles now, for particles, mass concentration is the only one of these that we will still use. It doesn't really make sense to talk about a mole fraction in ppm or even a molar concentration for particles. So we will use a mass concentration. Same units, typically milligram per meter cubed when we're talking about particles. So that's what our first concentration is for particles. But we also have another one that we'll use, and that is number concentration. So this is something new. And a number concentration is in terms of number of particles per meter cubed. Sometimes we just illustrate that with the pound sign, which can also mean number. So number of particles per meter cubed. And typically, since we have so many particles, we'll use millions of particles per meter cubed. That'll be our most usual one, actually. So just as a quick example, let's suppose that C number J is equal to 34.8 times 10 to the 7th particles per cubic meter, which is a huge number. We convert by multiplying by 10 to the negative 6. So we get C number J equal 348 million particles per cubic meter. And that's a more reasonable number to write, and that's why we typically have number concentration in millions of particles per meter cubed. In summary, we're going to use both mass concentration and number concentration. So we will have to learn how to convert between the two. Well, let's look at C number J. Again, it's the number of particles per volume by definition. We'll let NT be the number of particles. So this is NT over volume. And now let's multiply and divide by MP mean, the mean particle mass. But recall that MP mean, a mean particle mass, would just be the total mass divided by total number of particles. This would give us a mean particle mass or a mass per particle. So this equation becomes, if I use this definition for the numerator but keep the denominator there, I get this equation. And we see that the NTs cancel out. And we also see that this MT over volume is our definition of CJ, the mass concentration. So the bottom line is C number J, the number concentration, is the mass concentration CJ divided by MP mean. So this is our equation for conversion from mass concentration to number concentration. Now, we haven't really defined what MP mean is. We know that it's the total mass over the number of particles, the total number of particles. But in terms of some kind of particle diameter, let's define it this way. MP mean is rho p, this is the particle density, times pi dpam mass, I'll define that in a minute here, cubed over 6. And to the side here, I'll just write that the volume of a sphere, you should recall, in terms of diameter, is pi d cubed over 6. So that's what we're doing here. We're taking pi times this average diameter cubed over 6, but we haven't defined what that average diameter is. By the way, the p subscript means particle, so the rho p is density of the particle. Rho by itself, later on when we get to that, will just be the density of the air, which we sometimes call rho A, or we just leave it as rho. Now we need to find this dpam mass. So let me break this down into parts. dp, of course, means the particle diameter. It's a diameter with a subscript p, so that's the particle diameter. The AM means arithmetic mean, which is your common average. And then mass, this is the new thing that you probably haven't seen before, is that this whole diameter, dpam mass, is based on mass and rather than on diameter. So you see there's two different ways we can calculate an arithmetic mean of a particle, an arithmetic mean diameter. We can base it on the diameter itself, or we can base it on the mass of the particle, and those will be different. Note that even though we call this dpam mass, the mass in parentheses simply means that it's based on mass rather than on diameter. But the units of dpam mass are still microns. It's still a diameter. And you can also define dpam based on diameter rather than mass. And then that would also have typical units of microns. So let's just formally list these types of average diameters. We define dpam diameter as the mean particle diameter based on diameter. That's what this parentheses means here, based on diameter. And since this is an arithmetic mean, dpam diameter is the simple average that we all know and love. Basically, you add up all the particle diameters and divide by nt. So it's the sum over all particles of dp over total number of particles. So there's nothing new or unusual about that diameter. Now let's look at dpam based on mass. So again, by definition, this is the mean particle diameter based on mass instead of diameter. This one's a little more tricky. First, we need to calculate MP mean, which I already defined above. This is the mean particle mass, which is again a simple average, but it's of the masses instead of the diameters. So we define it as the sum over all the particles of the mass of each particle over nt. So we had defined a dpam diameter. Now we can define an MP mean as the mean mass of a particle. And now we can use this to calculate our dpam mass. So the question is, what is the diameter? This is the equivalent diameter that corresponds to this mean mass of a particle. So dpam mass is the mean particle diameter based on this mean mass that we just defined. So consider one of these average particles. So now we're talking about a particle that has this mean mass that we defined here. So MP mean is equal to rho of the particle times pi dpam mass cubed over 6, the volume of a sphere that has a diameter that's equal to dpam mass. So that's our equation for MP mean. Or we can rewrite this equation as dpam mass is equal to 6 MP mean over pi rho that quantity to the 1/3 power. Note that these two diameters, dpam diameter, is not equal to dpam mass. In fact, dpam diameter is less than dpam mass. Why? Because when you're taking an arithmetic mean based on diameter, this one is proportional to dp to the 1. Whereas when you're taking it based on mass, it's proportional to dp cubed. So the bigger particles have a lot more mass proportionally than the little particles do. And so dpam mass is a bigger number compared to dpam diameter. Finally, let's do an example of conversions. So in this problem, Veronica collects a small sample of dusty air, and the particle material has a density, rho p of 2340 kilogram per meter cubed. She runs her sample through a particle analyzer and finds the dPam mass is 12.3 microns. An optical instrument shows that the average number concentration is 456 million particles per cubic meter. We want to estimate the mass concentration of the particles in milligram per meter cubed to 3 significant digits. And we can work through this equation to solve for Cj, which is the mass concentration, which is what we want. So Cj is C number j times MP mean, and then plug in the second equation for MP mean, and we have C number j times rho p over 6 pi dPam mass cubed. And the rest is just plugging in the numbers and unit conversions. So we have 456 million particles per meter cubed is our number concentration. So I just wrote that all out here, 456 million particles per meter cubed. And then our density, 2340 kilogram per meter cubed over 6 pi. And then our dPam mass was 12.3 microns. Make sure you always convert microns into meters when you're doing these kinds of equations, or you'll be off by lots of factors of 10. And then just one unit conversion here, 10 to the 6 milligram per kilogram. And you can see that our meters cubed here cancels out with that meters cubed, and a kilogram cancels with a kilogram. So we should end up with milligrams per meter cubed, which is what we wanted. And when you plug this into your calculator, you should get 1040 milligram per meter cubed. So that's where I'll stop.
I must say that is a little bit confusing.
It may be a little confusing with these new strange particle diameter definitions and mean masses, but go through this a couple times if necessary to make sure you understand what these are. We'll be using these throughout the rest of the course, so you need to know what they mean.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.